Hi, my name is John Goodson, and I work at Industrial Light and Magic, and I'm a concept model maker for Episode 1, The Phantom Menace. I build things like this. The way that we make things like this look so real, a lot of it goes back to math. A lot of it is about proportions and scale of things, and we have to pay attention to make sure that things are symmetrical, things are round, things are the correct shapes and stuff, and a lot of that is based on math calculations and just paying attention to math details involved in it. Queen Amidala's starship looks a lot like the SR-71 because it was inspired by the SR-71. The SR-71 is a really sleek airplane with a lot of beautiful lines. It looks like it can go really, really fast. So Queen Amidala's ship has to look equally fast. It does look like it can go the speed of light. I hope you enjoyed this episode of NASA Connect. I hope seeing this will help to inspire you to pursue mathematics and science, and may the force of your imagination be with you.
Hi, I'm Van Hughes, and welcome to NASA Connect, the show that connects you with the world of math, science, and NASA. Well, right now, my band, The Noodles, is trying to get on the road to our next gig, but as you can see, we're having a little car trouble.
Man, these spools don't fit these bolts. There's no way we can finish this today.
We'll have to cancel another performance. I'll see you tomorrow. Yeah, Van, this old van has had it. See you later.
Guys? Guys! Hey, Jennifer. Thanks for coming over.
Sure, it's no problem. What's up with your van?
Okay, whenever we pack the van and we get onto the open road, the vibration is terrible, and the van keeps stalling. Well, I replaced and tightened some loose bolts, but it just doesn't work. It keeps struggling. The gas mileage is lousy. It barely even makes it up hills. We're always the slowest thing on the highway. It overheats. It's a slug.
Well, you know what? It seems like you got some problems here, definite problems, and I think I've got your first one down.
Okay.
Right here, this is a metric wrench, and you're using that with U.S. standard bolts. They're not going to fit. It's just not going to work. Now, your second problem seems a little tougher. Whew. This van, it just doesn't look too aerodynamic.
Well, I could get some proper wrenches from my dad, but okay, how do I check my aerodynamic problem?
You know, I have some friends over at NASA Langley Research Center in Hampton, Virginia. They know all about the science of aerodynamics and the measurement tools used in their research.
Well, great. Maybe they can help me find out what's exactly wrong with the van.
I bet they can. Hey, you. Before we head over to NASA Langley, let's learn more about measurement and why it's so important to measure accurately.
That's right. We'll check out a museum that will give us some background history on measurement.
And speaking of measurement, we have this really cool checklist for you to follow throughout our show. Every time our stage manager appears with a cue card, that's your cue to think about answers to the questions he gives you. Got it? Later, we'll go to NASA Langley in Hampton, Virginia, and NASA Dryden in California's Mojave Desert to meet some people who use measurement tools as part of their jobs designing and testing airplanes.
And, so you can get even more involved in measurement, you'll meet some students from Prince William County, Virginia, who will show you how to use measurement to build your own wind tunnel.
You'll also meet students from Ann Beers Elementary School in Washington, D.C., who are using FoilSim, a wind tunnel simulation, with NASA's Educational Technology Program Manager, Dr. Shelley Canwright. Students will show you how they are using the internet to learn more about the science of aerodynamics and how you can use our website to conduct your own simulated wind tunnel investigation.
So, Jennifer, are you ready?
Man, I was born ready. But be glad we're taking my car.
How did the U.S. Standard System of Measurement develop?
How is the metric system devised?
How are the two systems different?
Let's begin our measurement journey by visiting the Peninsula Fine Arts Center in Newport News, Virginia.
People have been measuring things for thousands of years. Hey, that's one thing we measure. Time. What are some of the other things we measure?
Temperature. How high is it? Volume. How much space is in your garage.
Madison, wait. How heavy is it? Length. How long is your street?
Get this. The ancient Egyptians used their fingers, hands, and even arms to measure things. There were no measuring tools like rulers back then. The width of one finger was a digit, and the width of 4 fingers was a palm.
Here's another ancient Egyptian measurement. Open your hand and spread out your fingers just like this. The distance from the tip of your thumb to the end of your little pinky was called a span.
The ancient Egyptians also created a measurement called the cubit. If you bend your arm, the distance from the elbow to the tip of your middle finger was a cubit. In the ancient world, the cubit was the most popular way to measure length.
So you see, all these units of measurement were based on something familiar to ancient people. Body parts.
Of course, using your hand or elbow to measure a pyramid would take forever.
Not only that, it's not an accurate or exact measurement. Here's why.
My friend Jimmy is taller than I am. It takes 4 of my cubic arm lengths, but only 3 of his to measure my butt. How can we get the same measurement if our arms are different lengths?
Good point. In ancient Egypt, it was up to the pharaoh to decide how to make measurements standard or the same for all situations.
So the standard cubit length was set by the length of the pharaoh's arm. But even then, it could be pretty tough measuring a pyramid with a pharaoh under your arm.
As time went on, people created many ways to measure things. Unfortunately, none of them were the same when it came to mathematics. You see, scientists couldn't repeat each other's experiments because there was not an agreed-upon standard of measurement. Today, our world operates according to 2 different systems of measurement. Here's some expert help.
In the U.S. standard system, the inch, foot, yard, and mile developed from traditional practices of measurement dating back to ancient times. One disadvantage of the U.S. standard system is the different size units often have no simple relationship to each other. For instance, there are 12 inches in a foot, 3 feet in a yard, 1,760 yards, or 5,280 feet in a mile.
Converting different units of measurement, like miles to inches, requires some math. Here's an example. It's about 431 miles from Los Angeles to San Francisco. To convert these miles into inches, simply multiply the number of miles, 431, by the number of feet in a mile, 5,280, by the number of inches in a foot, 12. 431 miles converts to 27,308,169 inches. Whew.
Using the decimal system is a much easier way to measure and change units. Because earlier systems of measuring units were so confusing, the decimal system was devised. This system is based on tens and multiples of tens. Tenth numbers, or decimals, are easier to use than the U.S. standard system, which is based on twelfths. One advantage of the decimal system is the decimal point. Depending upon where it is moved, whole numbers can become fractions or multiples of tens.
Thanks, Dr. Morgan. We now know why there is a metric system of measurement.
Yep, and the metric system is based on the meter. The original meter was not the length of someone's finger or arm. Instead, it represented 1/10,000,000th of the distance from the North Pole to the equator. Hey, the meter is the most widely used measurement system for scientific work. Using the metric system, we can easily convert units with some mental math. For example, we know Los Angeles is approximately 600 kilometers from San Francisco. Now, if we want to know that same distance in meters, for example, all we have to do is multiply by 1,000. Why? Because there's 1,000 meters in 1 kilometer. So you multiply 600 times 1,000 and you get 600,000 meters. 600 kilometers is the same as 600,000 meters.
The Egyptians would have appreciated the meter stick. It's better than a pharaoh's arm. Okay, Jennifer, I now know the difference between the U.S. standard system and the metric system, and why my wrench didn't fit the bolts, but you seem to think that my van has an aerodynamic problem. How can I measure that?
I'm glad you asked, Van. Hey guys, I have some friends over at NASA Langley Research Center in Hampton, Virginia. We're gonna meet some engineers, and they use tools and techniques every day to measure aerodynamics. Van, I'm gonna call ahead and get us cleared for the research laboratory. Is that all right? Hi, is Mike there?
Explain 4 forces which affect aircraft performance and how they relate to each other.
Dan, I want you to meet my friend. This is Mike Logan.
Hi.
Hi, Van.
He works here at NASA Langley Research Center in Hampton, Virginia, designing aircraft.
Wow.
So, Van, Jennifer tells me you're having a problem with your vehicle.
Oh, I sure am. I belong to a band called the Noodles, and we bought a van to carry our equipment to our performances, but it keeps breaking down. Jennifer says it might be an aerodynamic problem. Can you help?
Sure. We here at the NASA Langley Research Center have been studying aerodynamics since 1917.
Every aircraft is designed with a specific purpose in mind, like carrying people or cargo. No matter what the purpose is, all aircraft designs must consider 4 basic forces: lift, weight, thrust, and drag. Lift is the force that moves an airplane up when the air flows across the wings. Weight is the effect of gravity pulling an airplane down. The force that pushes a plane forward is called thrust. It's usually created by a plane's engines or propellers. The last force, drag, slows an airplane down as air rubs against the plane's surfaces. It's a lot like the friction created when a tire skids across the road. We measure these forces by creating scale models of our designs and then testing them in wind tunnels. At NASA Langley alone, we test designs in over 20 different wind tunnels.
So, Van, exactly what happens when you take your vehicle out?
Well, every time we load the equipment on top of the van, it doesn't have enough power. And every time we load our stuff inside the van, it helps a little, but it's still a slug.
Aerodynamically speaking, it sounds like you may be having a problem with drag, which is causing your engine to overwork. I think a wind tunnel test might help us to understand your problem better. I'll call a colleague of mine, Hector Soto, who designs measurement tools used in wind tunnels, and arrange for the two of you to meet. In the meantime, I'll go back to my office and work on some possible solutions to your problem.
Yeah.
What is a wind tunnel? How is a wind tunnel used as a measuring tool? Why is the SR-71 an ideal research test plane?
Hi, Jennifer.
Hi.
Hi, Van. Hi. Hey, Mike told me you might be having an aerodynamics problem with your vehicle.
We do.
Well, let me welcome you to my department, the Advanced Measurements and Diagnostics branch. Here we make tools to measure the performance of an aircraft in a wind tunnel.
No, a wind tunnel. Is that just like a big fan?
Well, let me explain what a wind tunnel is and how we use it to measure aerodynamic forces like drag. A wind tunnel is a device consisting of an enclosed passage through which air is driven by a fan. The heart of a wind tunnel is the test section, in which a scale model is supported in a controlled airstream that flows about the model, duplicating the air of the stream of a full-scale aircraft. We use different techniques to measure aerodynamic forces. Things like flow visualization, use smoke, and a laser light sheet. Sometimes we use oil or water instead of air and streams of dye to watch the vortices and other unusual phenomena. Surface deformations, such as wing flexing, can affect drag. Here at NASA Langley, one instrument that we designed projects a pattern laser light onto a surface of a model being studied. Later we compare photographs and measure the differences in the pattern light. These differences show changes in the shape of the wing surface that might be disrupting the airflow. We call this turbulence. Data are collected during the testing and checked for accuracy. Speaking of accuracy, it is not until an aircraft is flight tested in the real world that design efficiency can be fully verified. NASA does most of its flight testing at NASA Dryden and California Mojave Desert.
As an aeronautical engineer at NASA Dryden Flight Research Center, I'm interested in all the measurements that are made during test and flight research missions. Blackbirds are the world's fastest and highest flying jets. They cruise along at speeds over 2,000 miles per hour at heights over 24 kilometers or above 80,000 feet. That's so high that when I look out the airplane's window, the sky seems to be darker, even during the daylight. The SR-71's unique capabilities make it an ideal platform for aeronautical research and experiments that are beyond the reach of any other jet. All of these data, plus reports from the pilots, are compared with computer, wind tunnel, and flight simulator information so that engineers will understand exactly what is happening with the design.
So Van, these are just a few of the ways we measure aerodynamic forces. Hey, I have a friend of mine, Drew Landerman, that works at the Old Dominion University full-scale wind tunnel. Perhaps we could give him a call and arrange to have your vehicle tested. Let me explain.
Now, while those guys go test the van, let's meet some Prince William County math camp students who will use measurement to build a wind tunnel. In this activity, we'll determine the effect drag has on different shapes. And later, I'll be back and help you analyze the data.
Welcome to the Making Math Count enrichment camp at Saunders Middle School in Prince William County, Virginia. NASA Connect asked us to show you how to make and build your own wind tunnel and use it to test certain shapes for drag. Drag is one of the 4 forces that aeronautic engineers consider when they design airplanes. The other 3 forces are lift, weight, and thrust. Under the guidance of our teachers, Mr. Bill White, Miss Melinda Spencer, and Miss Trindle Miller, we will go through the steps you'll use in constructing your wind tunnel. Before you begin, go to this website to learn about wind tunnels. This will give you a good understanding about the measurement tool you're about to build.
After you've gotten your materials together, we begin by measuring the fan. Next, write the dimensions of the fan on the board. Each student should fill out the data sheet by determining the dimensions for the 8 trapezoid-shaped panels of the upper and lower sections of the wind tunnel and the 4 smaller rectangular panels of the test chamber. If the side of the fan is X, then the height and bottom width of the trapezoid shapes would be the same size and the top would be 1/3 of X or X over 3. The dimensions of the test chamber panels would be X over 2 for the height and X over 3 for the top and bottom. After checking the accuracy of the calculations, the teacher will divide the class into 4 teams.
Team 1, 2, and 3 will measure and mark their panels. The teacher will then cut the panels. The test chamber will fit between the upper and lower deflectors, so it is very important that the measuring and cutting is accurate, so the parts will fit together and be airtight. Team 1 will cut a window in one of the panels and tape a piece of transparency film over it from inside. Team 2 will cut a window in one of its panels and tape a piece of transparency film over it from the inside also. Now carefully tape the sections together, making sure that the windows are on the same side. When the wind tunnel is assembled, tape it to the box fan so then the air blows out of the bottom. Place the wind tunnel and fan onto 2 chairs like this. Make sure the chairs block as little airflow as possible.
To make the drag force test gauge, Team 4 cuts a 10 centimeter by 10 centimeter square card. Next, punch a 1 millimeter hole 3 centimeters from the top center of the card. Remove the elastic from inside the party hat and measure a 15 centimeter long piece. Do not stretch elastic when measuring. Double it over to form a loop. Thread the 2 loose ends through the hole in the card and tape them in place. Next, mark the center of the card. Beginning at the center point, draw a solid line to the right edge. Using 2 millimeter intervals, draw 5 lines above and below the center line that was just drawn. Using cardstock, cut an equilateral triangle with each side 2 centimeters in length. Cut 2 small slits in one side of the triangle and place our elastic through the slit, centering the measurement point of the triangle on the center line. While teams 1 through 4 are completing their assignments, use the templates to build the 4 polyhedrons, tetrahedron, pyramid, cube, and cone. Cut the shapes out, then bend along the dotted lines. Carefully tape the edges together to form the shapes. Tape string to the designated point on each shape. When the shape is suspended in the wind tunnel, it should be visible in the center of the test chamber. Now you are ready for testing. Before turning on the fan, note the position of the gauge. Start the fan on low speed. Count how many lines the gauge moves. Now increase the fan speed to medium. Count how many lines the gauge moves from its rest position. Do the same for high speed. The number of lines the gauge moves indicates the drag force exerted by the wind on the object. Run tests on the other polyhedrons. Record your results on the student data sheet. Now calculate the mean, median, and mode for each polyhedron at each speed. Using your results, make a graph. This will help you compare the drag force of each of the shapes. When all the data is collected and graphed, you are now ready to analyze the results.
Data analysis is one of the most important parts of an experiment. You know, this would be a great time for you to stop the video, use your thinker, and consider the following. Which factor, shape, mass, wind speed, or drag, is considered the constant? That means which of those factors stays the same throughout the entire experiment. And why is it important for this factor to remain constant? Look at your data. What relationship can you see between the shape of the object and the drag that's created? More questions like these and their answers can be found in the Educator's Guide. Teachers, you can download this from our NASA Connect website. Since we've been talking about wind tunnels, let's head over to Old Dominion University full-scale wind tunnel and see what Van's up to.
Hey, Drew.
Hello, Hector.
Jennifer, Van, this is Drew Landman.
Hi, Jennifer.
Hi, nice
Hi,
to meet you.
Van. Nice to meet you.
So, Drew, what do you have prepared for us?
Well, first, let me tell you a little bit about our wind tunnel. It's run by Old Dominion University in Norfolk, Virginia, and it's the second largest wind tunnel in the U.S. This full-scale tunnel was originally designed to test an entire aircraft. The fans at the end of the chute are 1,100 centimeters high. They can pull air through this test chamber at 133 kilometers per hour, or about 80 miles per hour. This creates enough wind for a small plane to achieve free flight testing within this facility. Not only do we test planes, but we also test NASCAR race cars. In fact, Van, we could test your vehicle.
Well, it's not going to fly away, is it?
No, we'll tie it down, and then we'll blow smoke over it to see how the air flows over it and how aerodynamically efficient it is. Let's get your van, Van.
Hey, let's check it out.
While Van prepares for the big test, let's find out how you can learn more about measuring in a wind tunnel with a special NASA connection to the web. Here's Dr. Shelley Canright to tell you more.
Well, thanks, Jennifer. I'm visiting a Space Science Academy, which is being held at Ian Beers Elementary School in Washington, D.C. This is a SEMA school. That stands for Science, Engineering, Mathematics, Aerospace Academy. It is an enrichment program that runs on weekends and in the summer and targets math, science, and technology. Its partner school is located in Cleveland, Ohio, Orchard Elementary School. In just a minute, we'll hear from a couple of these science campers as they demonstrate an interactive simulation software product called FoilSim. That's a special software created just for students by the Learning Technologies Project at NASA Glenn Research Center in Cleveland, Ohio. Now, if you look just behind me, you'll see a flight demonstration wind tunnel which some aeronautical engineering students from the American Institute of Aeronautics and Astronautics student branch at Iowa State University have brought to share with these younger students and to serve as mentors to the camp. So you can see the students here at Beers are getting the opportunity to try their hands on a number of technology research tools. Let's take a closer look now at one of those technologies, FoilSim. This is Alan Simmons, a 7th grade student at Dale Junior High.
Using FoilSim, we are able to use technologies like a NASA researcher. We could perform a series of computer-based wind tunnel tests on a wing using FoilSim. With this simulation, we can quickly change the position and shape of the wing and modify the airspeed, altitude, and angle of attack. And then FoilSim calculates the lift for us. We are quickly learning the factors that influence lift on an airplane's wing. Here is where we began, at the NASA Connect website. We were able to get set up by downloading and installing our own copy of FoilSim on our computer. Anyone can download this simulation and use it at school or at home. Let me show you how we've used FoilSim. We start out by learning about the basic aerodynamic forces that affect lift. Then we test out our own wing and learn how to generate lift. You can see how much lift we have generated during this test right here. After we've tested and learned about a bunch of different variables that affect lift, we got to work designing our own wing based on the requirements on the NASA Connect website. The last step is to create graphs of our experimental data and study them to see what things we can learn.
Jennifer, I think you would agree that these campers have given us some interesting highlights on how they are using technology to conduct experiments. A question for our viewers to think about is, what is the relationship between scientific inquiry and technology? Let me add, Jennifer, that our viewers are invited to try their hand with FoilSim by visiting the NASA Connect website. They will also find links to Kids Corner, where they will design and test paper airplane models, to a site about how wind tunnels are being used to improve NASCAR performance, and to information about NASA Connect online chats. There's also a career corner that features some of our program partners talking about their jobs. Well, I'm Shelley Canright reporting from Ann Beers Elementary School in Washington, D.C. Back to you, Jennifer.
Thanks a lot, Shelley. Well, a few moments ago, the van was lifted into the full-scale wind tunnel and prepped for the big test. As you can hear, the tunnel is on.
Van, look at all that turbulence.
No wonder my van is such a slug.
With all this turbulence, this thing will never move.
You see, Van, with all that equipment on top of your vehicle, it's like driving a refrigerator down the road. What you're creating is a great wall of resistance to the airflow.
Okay, Hector, so tell us then, what can we do to reduce this drag and get Van to his gigs on time?
What you can do is shape the equipment in a wedge shape so that would reduce the drag and help your vehicle slide through the air. Hey, everybody!
Hey there, Mike.
Hey, Mike, what you got there? What's that in your hand? Y'all come down and take a look. Great.
Okay, Mike, what do you have here?
Well, behold the van of the future.
You're kidding.
No, your van, like a refrigerator, is one of the worst aerodynamic shapes that a designer can work with. So I challenged myself. Can I make a van fly? And here you go.
All right.
By building a more aerodynamic shell onto the front and adding a tail, a rudder, and wings, I built this model from a computer design. I actually tested this design in NASA Langley's basic aerodynamic research tunnel.
Really? How did it go?
Surprisingly, it flew very well. So, Van, someday, you never know, you may be traveling in your very own flying minivan.
Wow, that'd be great. Never late again.
Well, that about wraps up this episode of NASA Connect. But before we go, we've got lots of people we need to thank, especially the students from Prince William County Math Camp and Ann Beers Elementary. Of course, we want to thank ODU, Hampton University, the NASA researchers, and Dr. Shelley Canright. If you would like a videotape copy of this NASA Connect show and the Educator's Guide lesson plans, contact CORE, the NASA Central Operation of Resources for Educators. All this information and more is located on the NASA Connect website. So, for Van and the rest of the NASA Connect crew, I'm Jennifer Pulley. You guys, where did Van go?
Hey guys, want to go do a show?
Hey, how'd you get this thing running?
Well, I measured it out.
What? Hey, Van, I didn't know you so handy with the socket wrench.
Well, what do you mean there? Metric or is that standard?
Man, what are you talking about?
Well, I can't take all the credit for getting this van running right. My friends at NASA helped me measure it all out, and they showed me a way that we might travel in the future.
Ladies and gentlemen, the Noodle!